Okay, good morning, everyone. So it's very nice to see that you're still here. Well, some of you at least, you know. Yeah, a couple of informations before we start today's session. So for lunch, we're not going to the dining hall today because it's closed. Those of you who got the lunch option will get a lunch box, okay? One tiny detail, maybe this is not gonna make you very happy, but for logistical reasons, we'll stop having coffee at noon. Okay, but wait. So it's because otherwise it was going to be really complicated for us. So someone is coming to get the coffee makers. There's a coffee dispenser in the hall. It's full. So if you want to get coffee, you can get it there, but then you'll have to pay for it. Basically, you know, it's like 60 cents or something like this. You know, like so it's only for this afternoon. So you'll get coffee. Don't worry, but it's just that you won't get it for free, and you won't have to go up upstairs in this room, which is probably going to be like 35 degrees Celsius today, right? At the end of the day, because we're not going to finish too late today, at the end of the day, we're supposed to have a closing ceremony for 30 minutes. It's not going to take 30 minutes, but we should take advantage of that slot to continue the discussion that we started yesterday about who's going to do this next year. And so you can keep thinking about it, you know, like if you're like, oh yeah, I really want to do it. So maybe jump in at the end of the day, you know, and we'll have basically an hour to talk. Okay, so and we can talk about that. We can talk about other things, you know, like but you should still stick around until the end, especially if you're interested in organizing Linux Audio Conference next year. So anyway, I'll hand the mic to Tommy, who's going to be chairing the session for today. We hope you have a good time this morning.
Okay, thank you, Romain. As Romain just said, thank you all for being here bright and early on a Saturday. If you've made it this far, indeed, if you were at gym as well, hats off to you for your attendance and for braving the heat wave. We have 3 more fascinating paper sessions today, and it is my pleasure to introduce the first of those. And on that note, I'm going to hand over to Albert Greff, who's going to tell us about Raptor, the random arpeggiator, version 7. Take it away.
Thank you, Tommy. Yes, this is a long-term project, which I've been working on off and on over many years. And I dedicate this talk to Clarence Barlow, a good friend, who suddenly and unexpectedly passed away 2 years ago. Without him, this project simply wouldn't exist because, Clarence was quite unusual as an accomplished composer and as a professor of composition, because he told everyone how he did it. And that's quite unusual, and I learned a lot from him, even though I wasn't technically his student. But this stuff that I'm describing now I'm forever indebted to him for that, and you'll see that many of his famous formulas will make an appearance in this presentation. And before I get technical, another bit of trivia, if I may. This LAC is special to me because I presented for the first time 20 years ago, pretty much exactly maybe two or 3 months plus 20 years ago. And you can see that in the photo on the left, which I did, Frank took, because Frank Neumann, he's been doing many photographs of all LACs over the years. And he did quite a few photographs of me. I'm quite proud of that because I brought quite a bit of equipment, MIDI guitar and everything. And that was a very early version of the program that I'm talking about today. It was still standalone, so it was written in some obscure programming language you probably never heard before, because it was the forerunner of Pure, called Q at the time. That has been well, it has fallen to bit rot because it had not enough bits. It was 32-bit, and I never ported it to 64. And so there's quite a time span there. So I worked on this, as I said, off and on, and not really permanently. But the latest version is pretty good and brings this whole project to a kind of close for me, and that's what I'm reporting on today. So I don't want to go into the history, but there used to be a thing called Raptor version 4, which is actually what you see on this photograph on the left if you squint very hardly. The basic idea of this entire project was to take Clarence's Autobus program, which was developed on Atari of all things. You can still download it from our website at my institute. There's the link in the slides. You just go there, and you need an Atari ST emulator, but I provide links for that as well. So this was started out as version 4. Well, don't ask me about version numbering. I've changed my version numbering themes countless times. But, well, the first version which kind of worked was this version 4, which I've just shown you. I then ported it to a Q's successor, which was the programming language Pure, which I also presented, I think, around 2009 maybe. And then I embarked on this project again when Robin was so kind to add an interface. Where is he? I've seen him already. Ah, there he is. So I'm very thankful for the opportunity to be able to port this to Ardor. So as you've heard from Robin himself, he made this interface, and he equipped it with the possibility to do DSP plugins which run in, where you can call a bit of Lua code in every cycle. And I will show that at the end of the presentation as well. So this was the motivation to start working on the thing again and get it working in Ardor. And then I backported that version to PD, and that is what I call version 7. That was actually completed last year, but I'm only presenting it now, so it's the first publication about this. So this is basically the Ardor version was a port of the V6 PD version, and then I backported it to PD, but I completely rewrote the patch and everything because I also added some improvements, and that's maybe the most important thing on this slide. So we have Ardor support now. This is also included in the Ardor distribution, thanks to Robin. And there's not just Raptor. Raptor is the most advanced thing, but it has many parameters. It's not for everyone. So I have two simpler versions as well. So I have the Barlow arpeggiator, which uses some of the technology in Raptor, but not all of it, and it's much easier to operate. And then the simple arpeggiator, which is just a basic arpeggiator. This is also, if you want to write your own arpeggiator, this might be a way to start it, because you just take the simple arpeggiator and then you equip it with whatever processing you need to do. So the improvements that I added, latch mode, an improved looper, that is also in the Ardor version, and the better and simplified user interface and MIDI learn capabilities and a much improved MIDI controller support. For instance, these launch pads here, we all love grid controllers. We heard about that yesterday. And yeah, so this is just supported in the PD version. In ADA, you don't need this because you have all the infrastructure with GUI and MIDI input and so on is already there. So I have special support for, I bought lots of controllers in the past few years, Novation controllers. I already had some controllers from Archive Professional, and then I bought some DJ controllers because I thought that might be interesting. I didn't bring that. You can do these usual scratch kind of things with Raptor if you work with loops, but I didn't bring that, so I won't show it today. I probably would mess up the demo anyway, so I'm not a great instrumentalist. And because I tend to still play the MIDI guitar, and I bought a pedal a MIDI controller for that to have the hands-free. The Nectar Pacer is a pretty nice one. I used the cheap Behringer one before, but they break down all the time. The Nectar Pacer is a really good piece of kit, and this is supported as well now. And yes, so I agonized over the question how to present this stuff to you. You can read up in the paper about the long list of parameters that Raptor has. I won't go into that here, but I will show some of the important parameters in the demo later on. But I did want to go a bit into the mathematics because that's not been published anywhere. I mean, they're the original formulas for Autobusk, which Clarence has written quite a few papers about, but I do it a bit differently, not very differently, but I wanted to document once and for all how I did it, and especially the indispensability stuff, which is related to rhythm. And these formulas are quite complicated, so I will try to explain them as good as I can here in this presentation. So the first thing that Clarence is known for are his harmonicity formulas. And these are actually quite simple, and they actually go back quite a long time. So the basic concept was already explored by Euler in his 1739 paper, yes, actually 18th century paper, when he was at St. Petersburg, the Tentamen Novae Theoriae Musicae Exercissimus Harmoniae Principiis Dilucidae Expositae. I'm no Latin speaker, so forgive me if I pronounce that incorrectly, but I think, yeah, the title is a bit longer. They had half the text in the title those days. And yeah, so the principle is quite simple. You decompose, you factorize your rational, your ratio, which describes the frequency interval, and then you get some prime factors, and then for each prime factor you assign a weight to it. This is what I've written down as G of P here, so P is prime. And then you just add up all the numbers. This is really easy better to explain in an example. Let's consider a major third. A major third in classical tuning theory is 5 to 4. So it's the ratio, it's a rational number. In our tuning system, this isn't a rational interval anymore because we use equal temperament, of course, today. But if you're working in Clarence's mindset, you just rationalize all the intervals so that you really know what you're working with. And if you take 5/4, then you need to decompose that into its prime factors. The two prime factors which we have here are 2 and 5. So it's a 5-limit interval, as the tuning specialists say. And then you apply this formula. So maybe we should do it with the Euler formula because that's simpler to understand. So I have one prime factor of 5, and we take with Euler's formula, we just take 5 minus 1, which is 4. And then you have 2 to the second power, 2 squared. You have 2 times the prime factor of 2. It doesn't matter whether it's in the denominator or in the numerator. You just count them as many times as they're there after you canceled out all common factors. So in the Euler formula would give you 2 minus 1, which is 1, but you have to add 2 of those, which would be 2, and we already calculated the 4. 4 plus 2 is 6. But the formula is a bit more complicated with Clarence's approach, which tends to be better because it differentiates various intervals which are measured the same in Euler's formula. That was a major criticism actually launched at him by musicologists of the time, or music theorists. I'm not sure whether musicology existed back then. But so you get a value of 8.4, which gives you a kind of harmonic disharmonicity, actually. So to calculate the harmonicities from these, you take, basically you take the reciprocal of this value, but I tend to add 1 to this, because otherwise you get infinities for the prime interval, which is 0 prime numbers, because it's just 1 to 1. So then you'd get infinity. In Clarence's theory, he deals with these infinities in some way. I didn't want to deal with that, so I just add 1 here, which actually is a kind of operation that Euler also did. So I'm in known waters there. And so for instance here, you can calculate it on a calculator yourself. You get 1 divided by 9.4. That would give you the harmonicity value, which is somewhere in the middle. So what you get here is a kind of heuristic approach to calculating harmonicities or disharmonicities. And these actually are, as I've proven, these disharmonicities actually give you a kind of metric on the space of scale points. So you can actually do multidimensional scaling with these metrics that you get there, and you will get a graphical representation. That's all been described in other papers I wrote. The justification for this is that we we get a kind of measure for the disharmonicity which kind of fits together with the theory of psychoacoustics. That's the stuff that was done originally by von Helmholtz and then later picked up by Plomb and Leveld in the 1960s. So I've calculated some of these formulas. I just put splines through the points, so these are not the splines themselves are not representative, but the points are actually where the disharmonicity values are. And if you take a look at those, then you see that the very disharmonious intervals, like the tritone, which is here, one possible tuning alternative, which funnily Plomb and Leveld left out of their thing. It's just not there in the graph. But for the other values, you see that the values that are computed according to Barlow's formula, they kind of line up. The Euler's graph doesn't come close, and it's quite bad for some intervals, like minor thirds and some derived intervals. It gives much too high harmonicity values. So this is one thing. But we have 2 parts also in Autobus, and I even made the connection between these 2, still took this further, because now we have to talk about Barlow rhythms or Barlow meters. and the value that he derives from, the values that he derives from them, which he calls indispensabilities. By the way, these prime disharmonicities he calls indigestibilities. Like most, I don't know why, but most computer music composers are great doing word puns. They like them a lot. So we have the indispensabilities, which gives you a kind of number theoretic sequence where you get exactly one value, so they're uniquely determined for each beat in a rhythm. So you basically what you do is you take the numerator of the time signature or the meter that you're dealing with, and you do it prime decomposition into prime factors again, and then you calculate those weights. And as you get unique values, you can do many manipulations with that. It's also number theoretically interesting sequence, but for our purposes, it's just a way to label all the beats in a rhythm and assign rhythmic importances or saliences to them. And that's what the indispensabilities are. So the higher the value, the more indispensable this beat will be so that you recognize the rhythm. And these weights can be used in many ways, but I mean, it's obvious that you can use them for the note velocities, you can use them for the probabilities, and as I do in the Raptor program, you can use them to modulate other parameters like harmonicities so that you get varying harmonicity bounds, for instance, for the different weight beats in a measure. So, okay, I should maybe have left out this, but I wanted to show the formula. And there's Clarence used to make this famous statement, frankly, I don't know where the formula came from, also when I asked him. And this later actually became a piece by one of his students. So this, he said this quite often. But of course, he did have some heuristic arguments how to construct this formula. I won't go into all the gory details here, but the idea is that you break everything down to prime indispensabilities, and then you calculate these prime indispensabilities and do some kind of weighted sum of these. And that's this formula here. And there's a recursion. And you break it down to some very simple cases, which is the prime number 2, prime number 3, and then there's a recursion formula. I actually wanted to explain this, but I was too slow in my presentation, and Tommy already gave me the sign that I need to move on. So I just skip over this. It's the reduction, the recursion is actually quite easy to understand, and you get some different meters for any kind of meter that you can imagine, and then you put all of this together to get the arpeggiator, which takes as input the meter, tempo, arpeggiator mode, and stuff like this, and calculates average harmonicities using also the indispensabilities. So that's how it works, basically, and I will now show you, and I need this sheet. So I'm just, as I said, I'm not really a great musician, so I can just show you how it basically works. I have some set here, which is already playing. This is using algo drums in the background because my Raptor isn't great at doing rhythms. But I will mute that now. So what you're hearing is actually Raptor playing. And I have some presets on tap here. I can play different chords. So I can switch between the different presets, and as for an arpeggiator, you have quite an unusual feature. If Raptor the harmonicity stuff is actually enabled. It can also play chords. Okay, this sounds a bit strange. If you know Clarence Barlow's music, then this should sound vaguely familiar. It can also be very tonal, but that depends on the parameters that you use. And oops, sorry about that. Need to check that I have. So the parameters which do the harmonicity thing are actually 4 different parameters. You have a minimum harmonicity. If you watch these numbers here, this is very small harmonicity, but you're still hearing tonal notes. And that's because I also have a preference parameter, harmonic preference parameter, which is something that Autobus doesn't have. And so I can change that. If I change the preference, I can have a very high preference, I can have a very low preference, and I can have anything in the middle, which where everything becomes atonal. And if you have a very low preference, it's actually antitonal. And you can also play with this parameter. There's one modulation which picks up the velocities, the indispensabilities, and uses these, and then you can change the preference. And if you change the preference to negative values, then you'll get low harmonicity on the weak on the strong pulses. And if you turn it up, there we go. You get this. You get much more harmonicity on the strong pulses. So you can vary this a lot, and I have various presets which illustrate these settings. And you can also turn off the Raptor thing if you don't want it. Then it becomes an ordinary arpeggiator. And you can also do these Barlow-esque things, like have some intertonal stuff. And of course, if you want to spice it up, then you just add some synthesizers. And add some drums and your beat making. So I think before Romain or Tommy just starts looking angry, I should stop now and take a few questions. Thank you.
Okay, thank you very much for that, Albert. Have we any questions? Let me just hand you the mic.
The entire thing is on GitHub. So if you, the chord stuff and so on actually belongs to the Algo Joggle demo stuff that Sophia presented on Thursday. And the Raptor itself is in its own Raptor 7 repository. And in both repositories, you have a LAC demo branch where exactly the stuff that I've been showing today is. And there are also quite a few readmes, also how you can work, and the custom modes are used for the launchpad and everything. Yes. Okay. And thanks for the question.
What's the main domain this is geared to? Is it geared towards live performance or composition or just exploration, inspiring yourself? Like, what's the most common way you use this tool?
Well, it's suitable for both. With Autobusk, you have only the compositional way because you completely program it beforehand. Basically, you can do that as well with with Raptor because you can sequence it, all the parameters and all the node input, and then you have a compositional tool. But you can also use it, as I've demonstrated, for live performances. I'm just not good enough at this kind of things to show it very comprehensively, but it's possible, yes.
I think we have time for one more. If there are any takers in the room. Okay, I have a quick one.
Yeah, I think I have to tear down my stuff.
Oh, okay, fair enough. Fair
Thanks
enough.
again, everybody.
Thank you, Albert. Thank you very much.
Just put it on my head. Thank you.
You guys ready? Yes. Okay, next up we have Hugues Caddy and Mathis Devidal, local boys, here to present real-time musical instruments recognition for scenography purposes. Take it away.
So hello everybody, and thank you to be there for this small presentation about real-time musical instrument recognition for scenography purposes. So this project took place in the context of an end-of-study academic project for our master at INSA Lyon, and I'll be presenting with Mathis. So to go through the big picture of the project, we'll deep dive in three main parts, starting with matrixing the project, or where did the idea come from. Then we'll go through more technical aspects of it, speaking of the preprocessing model and the metrics, and of course we'll conclude with the result and a small conclusion.
So thank you, Hugues. Let's dive into the maturating phase, where we are going to show you how did we get the idea. So we won't take too much time about this, but however, this is interesting to take a look at this. So the idea comes from myself. I don't know if this is a good point or not, but anyway, that's it. So in fact, I kind of love electronic music. And when you go, for example, on YouTube to listen for some electronic music, you have some cool visualizers on it. So you can see, for example, some FFTs, some spectrum, some frequency representation, and when you have real cool graphical effects reacting to the amplitude of some frequencies, especially in the lower frequencies. And I was wondering, is it possible to, instead of reacting to the amplitude of some frequencies, react to the presence of some instruments, or more specifically, synthesizers in the context of electronic music? So this was the initial idea, and for the more technical aspect of this, we are in the context where we do not have the separated tracks. Otherwise, there won't be any challenge. So we only have one waveform with the whole sounds in it. Then the question is how to detect the different instruments in there. And we had the idea to use artificial intelligence and more specifically deep learning techniques because we have seen that deep learning has showed some interesting results, for example, in computer vision, image recognition, and we wanted to see if this could be applied to music. So then the idea was born. We are going to talk a little bit about the scenography because this is a term that is present in our paper title. However, we have not studied very much that part. This is more a motivation for our work. So as described in our paper, scenography is designing and setting up the visual and spatial environment in which a performance takes place in order to support and enhance the artistic expression. In the context of music, and more specifically in the context of electronic music, when you see some DJ sets, for example, you can see some visual effects like lightning effects and even pyrotechnical effects. To do so, you can use a software called QLab, for example, which provides some cues to trigger these effects. For the moment, you can rather pre-program all the cues, which will be synchronized to some timestamps, or you can have a person which is manually triggering the different effects. So it means that everything needs to be known in advance and planned. With our solution, we can imagine of a possible to use the Cues API provided by the QLab software and interfacing with the detection of the instruments, provide for semi-improvised shows, for example, some scenography aspects. And this is particularly the case in electronic music, for example, because DJs do not know in advance what the different tracks will be played. So for the key challenges of our project, we have two main parts. We have a part about deep learning. So the first question was, is there such a data set? We need a data set which is huge enough in order to have enough music to train on it, and we need the music to be correctly labelized. We need to know at any point in time what are the instruments that are being played for a song. We also are in the context of multi-label classification, which is brandly new to us because we are in the context where we have a single label classification. We are more used to deal with this, but not with the multi-label context one. And of course, there is the question about the data representation, how to represent sound for a model to be able to process it. For the music part, we have a constraint of real time, we need speed. Because this is intended for scenography purposes, when you want to have the less possible latency. You do not want your public to distinguish between what they hear and what they can see, for example. And of course, we are in the polyphonic context, so it means that our model needs to be able, for example, to recognize the piano itself, and the piano with two instruments, the piano with three instruments, and so on, and so on. On top of that, we are in the context where we had limited time. As Hugues said earlier, we are in the context of a school project, so we do not have all the time that we can wander. And also we have limited resources. Especially for the training phase, we do not have access to HPC solutions or supercalculators and so on and so on. So for these challenges, we took some design decisions about the deep learning part. We decided to go for the dataset called LAC2025, which provides around 150 hours of music. And we had the different tracks with all the stems. So we had the separated instruments track. So this could allow us to generate new musics, but Hugues will explain this a bit later. We decided to focus our training on 5 instruments, so the drums, piano, brass, guitar, and bass. Why these 5 instruments? Because for the drums, you have very short sounds that can happen in all the frequencies. For the piano, you have something that happens in the mid-frequencies, for example. And the brass and the guitar are, let's say, a bit longer sounds that happens in always the mid-frequencies. And we wanted something that was long in terms of notes, but in the lower frequencies. That is why we decided to go for the bass also. For the data representation, we decided to go for an FFT. Why this choice? Because this is an idea that was provided to us. The idea is that if a human is able to distinguish between a bass and some piano, for example, in the bin frequencies on an FFT, so if a human is capable of doing it, so a model can be able to do it. So, about the music aspect, we decided to choose the Rust programming language. Why this language? Because firstly, this is a new language, so this was very motivating us. And this is a compiled language which provides fastness. You can be really fast with this language. And on top of that, it provides memory safety. So this is really useful, and you have some interesting methods and data structures and so on and so on. We decided to go for a simple CNN, so convolutional neural network architecture, which provides lightness and speed. Of course, we did not choose this architecture directly. We have gone through different choices, but Hugo will explain this a bit later.
So thanks much. So before going more thoroughly into the technical aspects of our project, we wanted to go through a brief state of the art. So basically what we started looking at was the music information retrieval that started in the 21st century. So the music information retrieval field of research, which was fastly followed by the RT-MIR, which added the real-time aspect of it, which is a core of our project. Then as early as the 2010s, several studies emerged, most of them based on CNN, so the architectures we focused on, but some alternatives exist, including, for instance, the hierarchical analysis. And this is with this information in mind that we continued our project. So to go through the technical aspects, let's start with the preprocessing, but of course with the needs of it. So Mathis already said about the dataset we used, so a huge one, more than 140 hours of music that represents almost 500 gigs after decompression. And that was a goal, of course, but also a constraint. We were working on, let's say, a sensible workstation running on Debian with an i7 processor, 32 gigs of RAM, and an A3000 GPU. So not an ultrabook, but a workstation. And we wanted to use it for the training and the inference. So now we can focus on the pipeline. So the goal behind it was obviously to make the training faster. So there is a lot to see here, but the important information to remember is that there are 4 main phases. The first one is the basic checking, a bit of cleaning. For instance, we don't train on the full data sets. We remove a part of it, including we remove songs and part of the songs themselves. Then we do checks on the chunks, some downsampling. So for the downsampling, you'll understand that the main focus we had, we always keep in mind how the human would do it, and we chose the factor 8 in our case, because this is the biggest factor we found to be recognizable after the downsampling by the human being at here. So we could still recognize the instruments as humans. Then we have the chunks operation, so basically a bit of cleaning, and that's what Mathis teased us earlier about this LAC dataset. Basically, we have the full mix, so with all the instruments, but one of the biggest advantages of SLAC is that it provides all the stems of each instrument, and so we can basically produce new mix with all the instruments we want to learn on, and not all the instruments. So for instance, the 5 instruments we focused on. After we have the balancing strategy I'll focus on later, and some data transformation. We compute the FFT, as stated, and we do a bit of normalization because of issues with at early stages of the training process. So as promised, a bit of balancing strategy. It is, in fact, very simple, very intuitive. Let's take an example with the 5 instruments we want to learn on. So basically, what we'll do in the first way is that we'll create 5 equal in size sub-datasets, and for each of these sub-datasets, we'll have, for instance, for the first one, 5 instruments by chunks, then for the second one, 4 instruments, etc., etc. And for each of these sub-datasets, so in the second phase, we'll keep in mind counters for the appearance of each instrument to have an almost equality of the appearing of each instrument with a small delta. Now that we built this pretty big pipeline, we can zoom on the model, so on the need. So as we stated a lot of times, the efficiency was the main goal because of the workstation we used, because it was, in fact, a goal we had in mind. We tested lots of architectures, including ResNet transformers. So all architectures based on the FFT results we had after the pipeline. But we had a lot of issues implementing them, and that's why in our constraints of time, we focused on basic, let's say, CNN architectures and ended up with an 8 layers CNN. So here is the global architectures of the model. So we have 4 double conv blocks that are basically 2 one-dimensional layers, followed by an activation layer to introduce non-linearity, a small dropout to help focusing on more complex features of the input data, and a bit of max pooling to reduce the output of such a layer. And of course, at the end, we have linear layers to give us the output vector with the instruments detected or not.
So thank you, Hugues. Now let's say 1 or 2 words about measuring the performance. In deep learning, one useful tool to measure performance is the confusion matrix. So you have an example in here. For the people who are not very familiar with this tool, this is a basic, let's say, mathematical matrix. You have on the rows the predicted classes or the predicted instruments in our case by the model, and on the columns you have the expected instruments or the expected classes for the sample you are currently trying to infer. So for example, if your model predicted 1 and you expected the instrument number 3, you will increase the brightness of the square identified by 1, 3. And of course, a matrix which displays good performance for a model is a matrix that contains only a white diagonal and darker squares elsewhere. From this tool, you can extract the accuracy and the F-score, more specifically the macro F-score, and we also had the EMR, or the exact match ratio, which is basically the ratio between the output vector, or the exact output vector of the expected one. So this is available in the single label classification context and not in the multi-label. That was our thought until we discovered this paper by Joan Herbany, who is unfortunately not here with us today, about confusion matrices, a unified theory. So he came up with a theory about confusion matrices that are based on the optimal transport mathematical theory that can provide us some confusion matrix for the multi-label classification context. And this is called TCM, so transport confusion matrix. From this tool, we can extract the accuracy and the macro F-score as we wanted. So now let's move on to the results, and before continuing, it has to be said that all the results that we're going to show you were obtained with the following training parameters. So we trained on 5 epochs, so one epoch is taking your whole dataset and passing it entirely through your network. So we do this 5 times, and this represented around 10 minutes of training. So we decided to choose also 70 seconds per track, so this gave us some batch of size 64, and we went for 186 milliseconds of samples to infer on it. Why this value? This is due to the sampling rate, the downsampling, and the FFT that Hugues explained a bit earlier. It has to be said that we found in some papers the value of 30 or 40 milliseconds, I cannot remember exactly, and we took this value as our chunk size. The goal of the 30-40 milliseconds is the acceptable threshold from which a human can distinguish between something is real time or not. But in fact, this was misinterpreted. This is not the size of the window we need to take, but this is the global time we need to take account for between the inputs of our model and the result of our model. We decide to space our chunks or samples evenly of 1 second to increase the diversity. We had in mind that if you take two samples that are too close together in the song, you won't have too much diversity. So we spaced them to have diversity. We ignored the first 10 seconds of the song to avoid some introduction effects. This is specifically the case in some electronic music. And we fixed the learning rate, which is a parameter used in the algorithm used to tweak the weights for your training phase to 1 × 10 to the power of -5. So now let's move on to the results. So here is the first table for the two instruments case with the piano and the drums. The interesting cells to look at are the cells identified by the maximum column and the test lines. So you can see that we are almost at 80% for the EMR, and we are also at 0.9 for the accuracy and F-score. Of course, we need to tend to 1 for the accuracy and both the F-score. So this is reasonably good results for the two instruments case. However, if we increase the number of instruments, for example, we input the guitar, we fall down to not even 8% for the EMR, and we oscillate between, let's say, 0.4 and 0.5 for both the accuracy and the F-score measures. We have some close results by replacing the guitar with the bass, for example. However, this is not really interesting to look at, but something which is interesting to look at are the TCM for the three instruments case. So on the left, you have the bass case, let's say, and on the right, you have the guitar case. One interesting thing to look at is that the piano is more confused with the bass than the piano and the guitar are. This is quite counterintuitive because bass and piano are much different than guitar and piano are. We know that this is a strange behavior that needs to be investigated, but as Hugues said, it was a school project and we didn't have that much time. To confirm the decrease in performance, we can take a look at the four instruments case where we fall down to not even 1% for the EMR, and we oscillate between 0.10 and 0.4 for accuracy and F-score. Final word to say about the training phase, you can see the loss evolution for both the training and the validation phase. You can see in blue the curve for the first epoch of the training phase. You can see that there is a decrease in the loss, which indicates that our model is actually learning something. However, if we take a look at the three instruments case, this tendency of decreasing in the loss is less and less seeable. You can less and less see it. And this is completely absent if you take a look at the four instruments case. So it shows that the more you increase the number of instruments, the less your model tends to learn.
So to conclude this presentation, of course, we wanted to talk about the future work. You may have understood that we worked a lot naively, intuitively during this project. So we took a step back at the end. So naively, still we could use the full data set because we use only a small subset of it to enhance performance. We could also choose to train on true instruments to push the project further because all of this data set is composed of synthetic music. But on top of that, I think that the most important thing we could learn from is basically all the fields of AI recognition and mostly speech recognition, which is really good working now and is mostly using temporal data instead of a frequential one. And I think that there is a thing to investigate here. So with Mathis, we are pretty proud of this preliminary work in a cutting-edge field. So of course, all of this project, including the code, the Rust code, the model produced during the project, and this defense are available on GitLab. And we wanted to thank a lot two persons that helped us a lot, so Romain Michon and Johan Erbani, that give us a lot of hints on their respective fields of research. So thanks for your attention, and do not hesitate if you have any question.
Thanks very much, gentlemen. Yes, questions for Hugues and Mathis?
Have you heard about Splitter? The stereo mix to multi-track splitting deep learning algorithm.
Yeah, we have heard about this. So you mean when you have some track and you use some algorithm to, in fact, split the different tracks? That's what you're talking about? Yeah.
Yeah.
Yeah, we have heard of this. However, as we had this constraint of real time, we feared that it will take too much time to, let's say, split the different things. As an example, I have a Hercule controller at home, and there is such an algorithm if you want to separate the different tracks on the fly, let's say, and this needs to pre-process the entire song before playing it. And if you don't have enough resources, the problem is that it will take too much time and you won't have this thing of real time. But yeah, we know that this is something that we can consider.
Yeah, of course it's more heavy because it is processing every chunk of audio.
Yeah.
But if you skip some samples, maybe it could work better. Or you can think of distilling the model to only output the signal presence, not the full audio.
Yeah, okay. Yeah, maybe this is something that we can try to investigate later. Yeah, you're right. Yeah.
Thank you.
Thank you.
Anyone else have a question? Yes, okay.
Thanks for your presentation. I'm a practical guy, so seeing tables with results is nice. Do you have any evidence of, say, playing back a musical piece and see the latency from playback to showing some FFT graphs, whatever, and also how well the instruments match what we see as graphs? Any video of that?
We have some demonstration. We have some videos.
Please.
We can show you. Yeah, for sure.
If we have time for that, sorry.
Yeah. Oops, sorry. We're just looking for the sound. Yeah. You can see there is some confusion between the piano and the drums, of course. But we have seen in all the different cases that our model is able to recognize the drums specifically. Yeah. You won't see better than this, unfortunately. Yeah.
Now, this specific audio file appeared to be a rather low sample rate or rather low bit rate. Was it intentional? It didn't sound like 16-bit 44.1 kilohertz to me. Would higher quality improve the quality of the detection?
Well, what you heard is actually what the model also heard here, because you have the downsampling factor. So this is intended to be not very high in terms of quality. So you can see that by here, with this downsampling factor of 8, you can, as a human, distinguish between the piano and the drums. And yeah, so this is also what the model hears. So that's why.
Okay. Yeah. Thanks a lot. I knew you had this at hand.
We have time for a couple more, if anyone's interested. Any takers? That looks like a hard no. Do I have something? I thought I did, but it's... Pardon? We have one. Good. Thank you for saving me, rescuing me from my terrible fate there. Oh, boy.
Have you thought of having a graphic representation of the instruments rather than just saying what they are?
Yeah, we can. I mean, initially we wanted to, for example, do this rather in Python because it was much easier to do it rather than Rust. But we have thoughts of, for example, displaying some I don't know, some forms with colors and some things that could, in fact, try to illustrate what scenography is, because, of course, when you see this, you do not see the aspect of the scenography. However, if you try to display some forms, some colors, and things like this, then you can see the scenography aspect of this. But yeah, we have thought of this, but however, as it was a school project, we did not have time to do it. So yeah, this is a fallback representation, basically, yeah.
One more, yes.
Did I get it right that you have a very short chunk size of actual data that you use, and then you wait for a second, and then you take another short chunk? Is that correct?
Yeah, there is a sliding window.
Yeah. That's, in fact, our chunks are almost 200 milliseconds.
Mm-hmm. So I just wanted to make sure that I got this right, because my question would be, if you're taking out of each note that each instrument plays a random chunk, then you might be missing the most characteristic traits. Like, for example, a trumpet tone, when it's begun and it's now sustaining, sounds like any other instrument that has begun and is now sustaining. So my question is, would it be feasible to look specifically at onsets of notes where you have the most, in terms of envelope, you have the most interesting things going on? Because I think that is also how humans differentiate. Because you could hear, for example, the confusion between drums and piano. The piano would use a constant chord that sounds exactly like a drum head if you don't look at the attack phase of it. So would it be possible to design something that in a pre-processing stage finds notes onsets and then focuses its analysis on the notes onsets and not use like a fixed window and a fixed spacing?
Yes, probably, and it would be a great solution, because in fact we focused on reducing the training time, but not specifically on improving, using the preprocessing pipeline, the training results. We got a lot of limitation, basically based on the fact that we do a lot of jumps between chunks. So we are not focused on the important information, and on top of that, we ignore a lot of it. So yes, there is really a field of improvement in this specific case.
I think that simply, for example, simply being synchronized on the tempo of the music would be very good. I think this is just. I think this is an easy step to improve the results also. But yeah, you're right. Yeah.
Okay, thank you very much, guys. Another round of applause for the gentleman. Okay, last but not least, everybody, we have Alexander Chalikiopoulos with Reviving the Heavy Compiler from Abandonment to Ownership.
Yes, so this talk about the heavy compiler will not be necessarily very technical. I want to speak more about how I sort of discovered the project, what its history is, and how we're moving forward in improving it. Yeah, so who am I? My background is actually in more like the hard sciences, molecular life sciences, and drug innovation, which is a track of pharmaceutical sciences. So not necessarily a programming background, but in university, like probably many of us, I got into Linux, not necessarily to the Linux user group, which was rather small niche in a corner of the uni, but through some friends. And I did do a minor in computer science, but that was very basic. Then I've been playing with FOSS audio and video since 2008. With some friends, we had a VJ team that we also developed our own software using Pure Data, but we mainly used GEM and PDIP and really worked on sort of the interactive video side of things. Then after academia, I was kind of disillusioned. either I would go for a PhD or work in pharmaceutical industry, which both was not really appealing to me. So I ended up becoming a backend developer and mainly using Python. So what is the heavy compiler? Maybe a show of hands who's already familiar. I think some of you are, but a very small percentage. So the heavy compiler is a data flow programming language compiler. So it will take a data flow patch and convert it into C, C++, and then you can build it and integrate it into everything that runs C. Its main input format right now is pure data, but theoretically it can use all kinds of other input formats. So the compiler itself is written in Python, but it uses an internal C library, just a heavy library that it will basically convert the patch in different stages. So first it interprets a patch file, then it will convert it into its own heavy format, which is basically a giant JSON file. And then it will convert it to an intermediate format that then is processed to generate a C project file that contains all of the DSP. So originally it was created by NGen Audio. I think they started development in 2012, but it was released in 2014. They came out of the RJDJ group, which was a group that made phone apps that ran with libpd, and it was sort of interactive phone applications. And I think they worked with several artists to develop patches for that. So NGen Audio was on the left Joe, on the right Joe White, and on the left Martin Roth. They basically developed the whole processing chain, and they ran their company NGen Audio to try and work with creatives to bring their patches to different frameworks. So the goal was to have efficient audio plugin development, because they ran into the limitations of running libpd on the phones, and they wanted to improve the performance. So they opted to try to convert the patch files into C and improve its performance, and then also to have creatives have a faster pipeline to go from their sort of prototyping phase to actual products. And then unfortunately in 2018 they decided to stop the project. They couldn't find a viable commercialization of it, and they open sourced it and then unfortunately abandoned the project. So it was kind of a code dump that they did, but luckily we could still find it. Then during COVID in 2021, I basically discovered the compiler, and my motivation was that with Mod Audio, who's familiar with Mod company? Some of you. So Mod basically ran an embedded Linux pedal board or pedal where you could connect LV2 plugins to design your own processing chains. So I knew that they had an integration with MaxGen, and so initially I wanted to see if I could get it to work. Of course, on the Linux it's not supported, so it took me a while to actually try and get it to run on the Linux. It mostly worked, except for the plugin manager. That's some Electron app that's integrated into it, and it couldn't actually download the mod plugin to do the LV2 generation. So it's kind of, not really happy with that. And after a month, the license expired, and I wasn't really interested to pay for something that doesn't support my platform. So I did remember the heavy compiler a little bit. During my time VJing with friends, we sort of found their platform, but because we were doing video and they were only targeting audio, we were not really interested in it at the time. But I did remember it, and I found the repository, and apparently, well, I didn't know they were open sourced, but apparently they did. And it was abandoned, but yeah, so basically I found it as a code dump. It wasn't really documented, there wasn't any history on the code, so only thing I knew is it was written in Python, and I knew Python, so I just started working on it. So basically what I had to do is at least migrate it from Python 2 to Python 3. It was quite outdated, so we needed to modernize it a bit. This was probably the easiest step. It was mainly changing some print statements, changing some imports, a couple of function calls like iterables that are different. But I got it to work on modern Python pretty quickly. Then I wanted to make it an actual Python module that would be installable. So instead of having to run scripts from the command line, So you'll see in the first couple of commits that I do is basically just organizing the code in a way that made it manageable and being able to install it as a Python module. And I submitted it to PyPy, so you could actually install the project easily. Then, of course, trying to understand how the code actually works was, and it still is, quite a challenge. There was some minimal documentation, mainly about the C library itself, so how the processing chain works and how its internal representation really works, but not really about the tool, the compile tool itself. And the structure was, very opinionated, let's say, on how they were using it and how they implemented it. So first things I did was just introduce some basic style and type checking, just so I would have some, before I started tweaking the code, I would have at least some, let's say, improved style and consistency in the code, so that I wouldn't necessarily break things or introduce changes that were not compatible. This is still ongoing, like it's not that I've all of the types introduced everywhere. There's a lot of dictionaries being passed back and forth, so I'm trying to move everything to pedantic classes, objects, so we have at least some understanding of the data types that are being used internally. And then I wanted to activate CI tests so that every time I change things that we would actually have some testing, so static integration steps, and then they had some tests already implemented, but it's also still ongoing to have a good coverage, of course. Then the main thing I wanted to do is actually improve, of course, and target the mod system that I wanted to use. So they had a plugin, a wrapper for the processing code that was based on the VC2 SDK. Now, as we all know, VC2 SDK has been abandoned or even, say, actively prohibited, let's say. You have to go to archive.org to find it, and officially you're not even allowed to use it because you can't get a license for it anymore. So what I did is move to the distro plugin framework, which I know Felipe, and we're in the chat, so it was quite easy to work with him to use it. And with that, of course, also came way more plugin formats. So instead of just VSC2, we get all of these for free, basically. And I think the last 3 ones were added in the last couple of years. But yeah, by going for plugin framework, we get a lot of extra plugin formats. So that makes it also nicer for the users to start using it. And what I didn't add is there's also Jack standalone, which I use a lot for testing, just because it's way easier than starting a plugin host. Then there were actually quite some sort of third-party developers that also did some bug fixes and had their own forks. There were pull requests open on the original repository, but since it was abandoned, nobody was actually merging them. So I went through all of these contributions, or as many as I could find, to try and integrate their fixes or their documentation extensions, or any new generators that they might have added. And then any of these inputs, I really wanted to make sure that it was available in the new version. And of course, needed to grow a community around the project, so making people aware that the project is still active, trying to contact any of these developers to try and get involved with the project. This is sometimes difficult because people also just do their own code dumps, or they're not easily accessible. And then the documentation, so there was a bunch of Markdown documentation, but yeah, it wasn't actually hosted anywhere, so through GitHub Pages, it was the easiest way to get it out there and have some documentation available for users. So there were definitely plenty of challenges, and still are. So technical hurdles in terms of legacy code. So let's say certain code structures that were not exactly modern, or as I said, sort of opinionated, or implemented in a specific way that was hard to work with. Outdated dependencies was not necessarily a big issue, at least for the compiler. It really only uses Jinja 2 as a templating engine, and for the rest, it's mostly straightforward Python. But there's some of the generators, they call it generators, it's a wrapper for the C code. And because they target many different systems, for instance, like game audio systems, so there's Unity wrappers and Wise, which is a middleware for game audio. These are all based on very old versions. So we had some users that were trying to use these different versions and they were no longer compatible. So that's because I don't have a background in Unity or game programming, that was tricky to deal with. Having backwards compatibility, of course, so that users could still use their own projects and we didn't want to change too many things about the system. And then in general, trying to connect with all these other projects and other tools to actually integrate with. Then in 2024, I had a meetup with the team, and basically it was sort of a semi-official transfer of ownership. So they decided, or also by my request, to archive their original repository because people were still posting issues there and trying to connect with them. So by them having an official archive of it and linking to my repo, that made it sort of more official, and that really felt like, okay, now it's sort of my project, now it's under my stewardship, which, it felt good to sort of be able to direct users, better direct users to my project. I did a split, like you can request at GitHub to split the hierarchy between repositories. So when you fork a repo, you will always point back to the original repository. But because I already had so many tickets, open, pull requests, project files, you can't really easily sort of transfer the ownership. So I had already requested basically splitting the repo. But yeah, having them forward to us, that was a big step. Then, key takeaways, it takes time. I mean, it takes time to understand the project, especially if it's complex. And because I don't have a DSP background, I had to learn a lot from it. It takes time to wait for other developers to respond, to connect with others. So sometimes you just have to wait it out, and then before you know it, things start moving. And yeah, there are many moving parts. Like I said, there's many different integrations, and yeah, if you don't really know how all of them work, it's hard to sort of wrap your head around all of it. And then collaboration is definitely key to try and find other knowledgeable people and try to connect with both users and other projects. So definitely the challenges are both technical but also human and community related. And in that sense, sort of open source stewardship, like really bring forward existing projects is important, and not just abandon things or do things in your own corner, let's say. So where does the project stand today? As was already presented before, and Timothy's also here, is the Plug Data project, which is sort of a re-envisioning of the user experience around PD. And I think Tim started around the same time as I did during COVID by working on this project. And I think it's probably like 2.5 years ago, found out that he's actually living like 30 minutes away from me. So that was quite a nice surprise, and we were able to actually meet up and discuss a bit like how we could collaborate, how we could maybe integrate the tools together. So in the Plug Data project, there is now a compiled mode, because one issue that a lot of users have is that the heavy compiler only supports like a subset of the vanilla objects. So a lot of users will open tickets or come with requests like, oh, I get errors when I use a certain object or when I use it in a certain way. And with this compiled mode, it will give you some warnings. Or also the tab completion that's available in Plug Data, it will only tab complete those supported objects. So that really helps a lot of users to get started, so they don't run into these issues of all these incompatible objects that they might use. So that's really nice. And then Tim and I hacked together a toolchain that is sort of independent of the OS, so that you can run it both on Linux, macOS, and Windows. And basically, it's a pre-assembled set of tools to be able to build. It's not ideal because, I think on macOS it probably works the best because we can use some OS hooks to just install all of the tools directly. Then for Windows, we have a sort of a packaged version of MingW to be able to have a GCC shell and do all the build in there. But for Linux, it's tricky because, of course, most distros, they have their own build tools that you could use, but to hook into every single distro and try to install all of the packages is quite tedious to maintain and quite difficult to do. So Tim found a project called Build Anywhere, which in theory is kind of nice, but it's very outdated. So I think it uses GCC 8 or 9 or something, so it's quite old. It has a lot of cruft, so a lot of tools that we don't need, so we have to remove all of those. It's not available for ARM, so right now we cannot, so for instance, we have users on Raspberry Pi with plug data, but they cannot use the compiler. So this is something that we're still looking to improve later, but it's quite seamless for most users. So you download the toolchain once or when there's an update, and then you have a bunch of compile options, and you can use the heavy compiler directly. And then, of course, coming back to Mod, they are now hosting a version of the compiler on their own cloud infrastructure. So users can upload PD patches there, and they can immediately load an LV2 plugin onto their device. So that's really cool. Rebel Technology, who does the OWL board, also an STM32-based prototyping environment, they're still using a fork that they developed. So that's still a fork of the old project. So that's still on their own cloud infrastructure. But we actually also support it. I basically just took all of their changes and imported it. And we have it directly in the plug data toolchain as well. So we can target these OWL boards directly from the editor. And same is for Electrosmith, which was also presented yesterday with the DAISY. So we can target microcontrollers directly from the PD editor. So that's also really cool. Then, of course, there's still plenty of improvements to make. Probably the biggest requested feature is having expressions. So PD, you have both control and signal rate expressions that are quite useful to do more advanced mathematics and have a lot of functions that are not available as regular PD objects. 2 years ago, a user saw the thread that we had on the issue thread, and they basically decided, okay, I'll take a stab at it, and they got quite far with the crude prototype of it, but then they kind of disappeared. So this year I tried to pick up their work and update it to the latest version, and just started writing tests and try to fix bugs. So we're quite far with this actually. So we have all control objects, or control expressions are mostly working, except for like frequency to MIDI and DB to RMS and these kind of objects, but you can already use them in PD anyway. And in the signal rate, it's still a little bit tricky, because in the heavy compiler, there's also SIMD optimizations. So there is a naive implementation that runs single sample, and then there's both Neon, SSE, and AVX implementations, and some of them are either buggy or lacking functional implementations. So right now, the focus is to have the single sample running, so that we can also use it on the embedded boards. And yeah, so how this benefits developers and musicians is mainly that you can also have users that are not necessarily C programmers, but they're able to still build a product. So on the left, we have Clatters machines. They're a small modular company from Italy, and I met them at Superboot, kind of unexpectedly. And they had designed a whole modular product from scratch without writing a single line of C, because they were using the PD patches, and they were able to design the electronics, and they managed to build a whole product around it. So that's really cool. And on the right is my own plugins that I'm now developing. They're pretty basic patch-wise, but it was a whole process to actually learn how to do this, how to build UIs, etc. So yeah, abandoned projects still matter, I'd say, and don't just let them rot away. So, of course, we can find open source abandoned projects and sort of scrap them for parts, but I'd say it's even better if we can find a way to maintain them and build a community around them, contact the original developers, and keep them alive. So I do hope that more devs will actually take ownership of these dormant projects, because we can learn a lot from them, and if there's established users and community around it, then it's it's good to keep things alive. So yeah, how to approach legacy code bases, just start somewhere, I'd say. Like I said, I don't really have a background in C development, maybe a little bit of Arduino here and there, and I know how to sort of force a compiler to get through. But yeah, start anywhere, cleaning up the code, writing documentation. You know, it's you'll learn along the way. So yeah, and try to build a community because it helps to find other people with maybe that knowledge that you're missing and fill in the gaps. So we've had many positive interactions, mainly with users, but also other developers. Many challenges, and then here also with the Plug Data team, we met up with some students that actually convinced their teachers to switch from pure data to Plug Data, and they're also using the toolchain to build their own prototypes, etc. So that's probably the best part of this, is that we're actually growing a community around it and making other people happy and getting more projects out there. So call to action: get involved in open source development, and how you can contribute is, well, read the code. We have a bunch of tickets that still need some help, so I'm always looking for people that maybe can fill in some of the gaps. Well, thank you, LAC, and maybe there's some questions. I can maybe do a demo. I don't know how much time there is.
If you've got something very quick, yeah. We've probably got 5 minutes for questions, 2 for demos.
Let's do questions first.
Okay. Well, a round of applause first. Thank you very much, Alexander, for that tale of that heartwarming tale of resurrection and community. How wonderful. Okay, we have a question. Great.
First, bravo for doing all that hard work, and it's really nice to see, this kind of work happening. But my question is more general, not really specific to, but somehow about the ecosystem around PD. I mean, we have people like Albert who contributes a lot to it, and from someone, I mean, I know about PD, I've used and taught some, but. From an outside perspective, not a daily user, it's quite confusing to understand, what goes on, because it seems there's so many forks, extensions, packages and stuff, and one runs in one, another one doesn't run in the other, and that kind of thing. Isn't there a way that you can rally the community to, well, let's unify this thing? I mean, actually what you're doing there with Plug Data sounds like a good beginning. But like, let's say, I switched from, PD to Plug Data. That doesn't sound like to me, it's like, oh, wow, I mean, it should be one, And as I say, we're here, some of us are kind of aging, and we have seen this before, with other projects. It was, just to give you an idea, well, I didn't speak about that yesterday, but between 98 and about 2002, there were like zillions versions and forks of C-Sound. And then everything coursed into C-Sound late water keep against C-Sound 5, and there's only one. But, it would be interesting to maybe that conversation is happening, but see, from the outside, it's quite confusing. But anyway, this is really good work, and I'm, pleased to see it. Thank you.
Yeah, so I do think that indeed the amount of PD forks have always been a little bit confusing, also to me. I do think that sort of PD vanilla is, of course, Miller's project, and it's, I mean, on the one hand, you could say he's very conservative, but I think that's a good thing in a way, because it's a very stable base, and, its backwards compatibility is really good, so that's good to have that as the base. In the case of Plug Data, it uses libpd directly, so it is, I think, in essence, fully compatible with PD itself. So patches can be used in between. So I think that's really good. Yeah, with the case with externals, it has always been a little bit tricky when we still had PD extended, and then now with the package manager in PD, it makes it a lot easier, I think. But then still, not all packages are available there. So yeah, I think that's always tricky. And then, yeah, I don't think that forking is necessarily bad. Like sometimes you just have a different opinion than the original developer and you want to do things differently, and then that's fine, you know. But especially like in this case where we have the sort of abandoned projects that are still out there, that's sort of more the focus of this talk, that, you know, try to rally around those to keep them alive rather than just, oh, I'll do my own fork and go somewhere else, you know. But yeah, the case of the PD forks, I think, yeah, there's other people with different opinions maybe on how to deal with that. In our case, with Heavy, it's vanilla only, so probably it works on all the forks. You can use the same patches as long as you stick to the right objects. So, yeah.
Maybe to add a bit oil to the fire. It used to be much worse with the PD forks. And now we have a couple which are pretty well established. I mean, vanilla, almost everyone uses vanilla, even those who use other forks. But I wanted to say, actually, thank you very much. I had a student a few years back, which she wanted to use the Heavy compiler because she was doing something with the Unreal Engine. And at that point, the Heavy compiler had fallen into disrepair. So we had to find another solution, and I'm glad that the project is back. Also, thanks to Tim, because he also was involved in that process.
Yeah.
Right. Thank you.
Yeah, and I think for users, so plug data, it's still PD under the hood. It's sort of, it's hard to call it really a fork. I mean, it tracks PD very closely. It's really the user experience around it, and that allows us to add sort of these extensions like the compiled mode or integrate the compiler itself. And especially for beginning users, that helps a lot to get started and to not fall into some of the traps that are there. Yeah, I think we're out of time, so hit me up if you have more to talk about. So thanks again.
Thank you, Alexander.
Thank you, Tommy. Thank you to the speakers. So we're going to have coffee break now. Coffee is ready upstairs. Enjoy it while you can. And yeah, we'll see you in 30 minutes.